All right, everybody, welcome to Math with Grace. Today we're going to be working through Pre-Calculus Unit 5, Section 2. Unit 2 begins on page 30, and it's titled More Identities, and we're starting with double angle formulas. It says, doubling an angle measure is the same as adding the measure to itself. Therefore, you can derive formulas for trig functions that double an angle measure by writing a sum. Okay, so they're starting with, and we're going to kind of look at how they derived it, and then we're just going to look at the actual formulas as we go, okay? So they're looking at the cosine function. So we're talking about a double angle, so they have the cosine of theta plus the cosine of theta, right? And they are working their way through, and they got to the point where the cosine of 2 theta was equal to cosine squared of theta minus sine squared of theta, okay? Piece of cake, okay? This double angle formula can be written in terms of just cosine or sine by using the Pythagorean identities, cosine squared plus sine squared equals 1. So there are 3 parts right here to the double angle cosine formulas. This is the first part, okay? Cosine 2 theta is equal to cosine squared minus sine squared. But you can change it and have them be either all sine or all cosine by using the Pythagorean formula, okay? Pythagorean identity. And so they did one here where they switched it over to sine so that the cosine of 2 theta is equal to 1 minus 2 times the sine squared of theta. And then they did it over here with the cosine so that the cosine of 2 theta is equal to 2 times the cosine squared of theta minus 1. And so now they have these 3 formulas for a double angle. We'll slide up to the top of page 31 to look at our first example. And it says here, if beta is a first quarter angle, okay, so over here, in standard position whose terminal side passes through the point 3, 4, so we went over 3 and up 4, right? So that's our x is the 3 and the y is the 4, which is apparent here from our ordered pair, right? Find the cosine of 2 beta. So you would need to choose which of the 3 formulas you want to use. But what they did here was they did all 3. So by sketching their angle, they were able to come up with the cosine and the sine, okay? By, of course, finding the hypotenuse of this right triangle, right? We've used this one a lot. It's a 3, 4, 5 triangle, so it probably didn't take too much, but you could have used the Pythagorean theorem to solve for the hypotenuse, right? Then you could find the cosine and the sine of beta, and then put it into the formulas, whichever one you choose. So if you do the cosine squared minus the sine squared, it's going to look like this. It's the shortest one, so maybe that was the best one to stick with, but you needed the most information, okay? 2 times the cosine squared minus 1. Of course, they're all going to come up to the same answer. Or 1 minus 2 times the sine squared was this one, right? So here is the process for each one. The answer is -7 over 25. It is a choice. You can choose which formula you would like to use. As I said, this original formula requires the most information, but it was also the shortest one to achieve, right? Where this one only requires one piece of information, but then we have to add or subtract fractions here. And so if you're not great at that, I mean, we're adding and subtracting fractions here too. So if you're not great at that, it's time to polish it up. The difference, I guess, with the original formula is automatically they should have the common denominator, and the adding or subtracting, in this case subtracting, would be easier. Where here, obviously, you're working with a whole number and a fraction, so you're going to have to adjust things. Okay? Now, it says, in a similar manner, you can derive the double angle formula for the sine and the tangent function. So they show it here. We're just going to look at the formula. So the double angle formula for the sine is the sine of 2 theta is equal to 2 times the sine times the cosine. So all these things multiply together. The double angle formula for the tangent is the tangent of 2 theta equals 2 times the tangent of theta divided by the quantity 1 minus tangent squared theta. Okay, so the tangent one's always a little bit more complicated. Let's take a look at a couple of these examples. For this first example on page 31, second column, it said if beta is a first quadrant angle in the standard position whose terminal side passes again through the point 34, find the sine of 2 betas. Okay, well, they've only given us one formula for that at this point. And so again, they graphed it. They found their sine and cosine because you need both pieces of information for this formula. So to use the double angle formula, it's 2 sine times cosine. And so they just put the fractions in and multiplied it out. 24 over 25. Okay. For this next example, they want us to find the tangent. If x equals pi over 6, find the tangent of 2x. Now, pi over 6 is a special angle, so let's grab our unit circle. All right, so remember, this unit circle is from unit 2. I don't remember the page number, I didn't write it down, but it is in the very back of the book. So, pi over 6, here's my unit, my radian, pi over 6 on my circle, right? Find the tangent. Well, they have the cosine and the sine. Remember, in this set of parentheses, we have, oh, goodness gracious, we have cosine, comma, sine. All right, so the tangent formula, the tangent of pi over 6, it's saying, again, we could use this chart for that, is square root of 3 over 3. This chart is in unit 3, page 75, square root of 3 over 3. It says use the double tangent formula to solve for this. I guess tangent was all we needed. We didn't use the unit circle this time, but this chart was useful. If you don't remember these things, not all of us have a memory like that, right? So use the information that they gave us. This one is from unit 3, page 75. So the tangent of the pi over 6 is square root of 3 over 3. We put that into our tangent formula, which they didn't rewrite this time. But remember, it is 2 times the tangent of theta over 1 minus the tangent squared of theta. So here they have 2 times the quantity square root of 3 over 3 over the quantity 1 minus the square root of 3 over 3, the quantity squared. Okay. Now remember, when we square a square root, the square root just drops away. But also remember, I don't see this as being an issue, but remember, we cannot have a square root in the denominator. It's not going to matter here because we're squaring things, but just keep that in mind. And they get their answer whittled down to 3. Remember, at this stage, we cannot divide a fraction by a fraction, so it's 2 times the square root of 3 over 3, and then we have to flip-flop multiply, or we have to multiply by the reciprocal of the denominator, which would be 3 over 2. My 3's and my 2's cancel, and that's how they got to the square root of 3, okay? All right, let's turn the page. Here at the top of page 32, it says that in addition to evaluating trigonometric functions, the double angle formula can be used in the process of proving identities. So if we wanted to prove here that the tangent of theta was plus the cotangent of 2 theta is equal to the cosecant of 2 theta, we could use our new formulas. So it says, let's first express everything in terms of sine and cosine. So they've changed all these around to sine and cosine. The tangent became sine over cosine. The cotangent of 2 theta became the cosine of 2 theta over the sine of 2 theta. And the cosecant of 2 theta became 1 over the sine of 2 theta. Okay, so we have to remember our identities. What's nice about this book, right, is in the back of this book, which I have yet to photocopy, but I will be, are all of our identities. Okay, so here's the reciprocal identities, the quotient identities, starting on page 43. The Pythagorean ones, all of them are here, even the new double angle and half angle, which we're about to talk about, okay? So these pages are super, super valuable in doing this work. I would suggest either keeping them on hand or making a copy for yourself. Okay, back to it, all right? It says use the double angle formulas to substitute for sine of 2 theta. So here, down here, the sine of 2 theta, the sine of 2 theta, right? They put in the formula for the sine of 2 theta. Then it says on the left, they got a common denominator. So the common denominator for the left is going to be 2 sine times cosine. We only have a cosine here, so they'd had to multiply this first term by 2 sine, okay? And that's how they got this 2 sine squared, plus the cosine of 2 theta over 2 sine cosine. And I have 2 sine cosine over here already as well. So now our denominators are the same, but we need the numerator to be a 1. This numerator here, we need it to be a 1. So it says use the double angle formula. Cosine of 2 theta is equal to 1 minus 2 sine squared of theta. So this cosine of 2 theta, the second half here, they substituted in 1 minus 2 sine squared of theta. Well, 2 sine squared of theta minus 2 sine squared of theta is 0. And so we're left with just the 1, and they are then identical, right? That's the whole point of an identity, is making one equal to the other. Okay. In order to solve some trig equations, it may be necessary to make substitutions using a double angle formula. So here we're actually trying to solve sine of 2x equals 3 times the sine of x for this range, right? Or not range, for this domain, right? From x is from 0 to 360. So that also tells us the unit that we're going to be using. We're going to be using degrees instead of radians. So these aren't really like things. They're not like terms, so we can't combine them or anything. So let's make a substitution using a double angle formula for sine. This is the sine of 2 theta, basically 2x. We can substitute in the formula. So it changes this to 2 sine of x cosine of x, okay? Now we have like terms. So we set the equation equal to 0 by moving this 3 sine of x across the equal sign. We factor out the sine of x that both terms have in common, and we're left with 2 cosine of x minus 3. Or, well, we're left with sine of x times the quantity, 2 cosine of x minus 3. We set each of these equal to 0, this equal to 0, and this equal to 0. And they found that the sine of x equals 0, or the cosine of x is 3 over 2. Since the cosine of x cannot be greater than 1, then there is no solution for this. This is not an actual solution. Therefore, the solution set is anywhere that the sine of x equals 0. And so on your unit circle, the sine of x equals 0 at 1, and the sine of x equals 0 at 180 degrees. Okay, those two places solve this problem. All right, okay, let's do a couple of these together. Here on page 33, it says, if theta is an angle in the standard position whose terminal side passes through the point 4, 3, then the tangent of 2 theta equals. All right, I like to write these down personally. It makes it easier for me. Standard position, terminal side passes through. Okay. Point 3, 4. So it's up here, and this is a 4. But again, this is still our 3, 4, 5 triangle, right? But the tangent, we didn't really need to draw this out for that, because remember, the tangent is opposite over adjacent. So the tangent in this case, and I like to draw it anyway because it helps me to see it, is 4 over 3. Okay, sorry about that. I'm hitting my water bottle. The tangent is 4 over 3. Okay, so the tangent of 2 theta, we need to use that formula, which is 2 tangent over 1 minus tangent squared, right? Okay, here's our tangent. So we have 2 times 4 over 3 all over 1 minus 4 over 3, the quantity squared. Okay. In the numerator, we end up with 8 over 3 over 1 minus, we'll get to this, the fractiony part in a second, 16 over 9. Remember, when you're squaring a fraction, you square the numerator and the denominator. So 16 over 9. To add these or subtract these fractions, right, my 1 is going to become a 9 over 9 because that is 1, right? 9 over 9 is 1. We're not changing the problem. So we have 8 over 3 divided by, they do not give us enough room to do the work in this book. It's crazy. 8 over 3 divided by 9 minus 16, because remember we're adding and subtracting a fraction. You only add or subtract the numerator, right? And my 9 rule tells me that this is going to be a negative 7 over 9. Now I can't divide a fraction by a fraction, so I'm going to have 8 over 3 flip-flop multiply, or multiply by the reciprocal, which is going to be negative 9 over 7. Now I can reduce here. 3 goes into 3 one time and into 9 3 times. And then I end up with, goodness gracious, negative 24 sevenths this is, okay? And that is not a choice. We've got 24 sevenths without the negative. Hold on a second. Taking a look at problem 2.2 on page 33. It says, if theta is an angle in standard position whose terminal side passes through the point 4, 3, then the tangent of 2 theta is, well, if I draw my angle here, and I'm going over 4 and up 3, that's where my point is, right? Over 4, up 3, that's where we are. This is my angle. The hypotenuse here would be 5, but it doesn't matter because we're talking about a tangent. So the tangent of theta, in this case, is going to be opposite over adjacent, which is 3 over 4. Now we can jump into the formula. Remember, it is 2 times the tangent of theta over 1 minus the tangent squared of theta. Okay? So I have 2, what's my tangent? 3 over 4. Over 1 minus 3 over 4, the quantity squared, okay? In the numerator, I'm going to end up with, this is going to reduce and become a 2, right? I'm going to end up with 3 over 2. And in the denominator, I'm going to have 1 minus 9 over 16. Remember, when you're squaring a fraction, you square the numerator and the denominator. And then we need to actually do the math on this fraction, right? So 1 is going to become 16 over 16 because 16 over 16 is 1, and I'm using 16 because my other denominator is also 16. So 16 minus 9 is 7. My numerator is 3 over 2. Is 7, and then the 16 is going to stay. Now, I cannot divide a fraction by a fraction, so I am going to take my numerator and then flip-flop multiply the denominator, or multiply by the reciprocal of my denominator. So it's going to look like this, right? I can reduce here this 2 with this 16 becomes an 8, and then my numerator I multiply across, so 24, and my denominator across is 7. 24 over 7, which is letter D. Okay. For number 3, it says, if cosine theta equals 3 over 5, and theta is located in the 4th quadrant, and now remember, in the 4th quadrant, my cosine is positive, then the sine of 2 theta is what? Well, because we have the triangle set up right here pretty much already, I mean, I'll redraw it, that's fine. They're using this 3, 4, 5 triangle pretty heavily. The cosine is 3 over 5, okay? That tells me that my adjacent is 3 and my hypotenuse is 5. So 5 here, the adjacent is here, okay? This is a negative 4 then, because that's just, it's a 3, 4, 5 triangle. So the cosine is adjacent over hypotenuse, and so that's what we have here, 3 over 5. That's how we can figure it out in our drawing. Now they want us to use the sine of 2 theta, so the sine in this case is opposite over hypotenuse, or negative 4 over 5, okay? Because the sine in this quadrant, quadrant 4, is negative. Now, for the sine of 2 theta, remember it is, oh, they gave us even less room on this one. All right, it is 2 times the sine of theta times the cosine of theta. So we needed both. We need both the cosine and the sine. So I have 2 times the sine, which is negative 4 over 5, times the cosine, which is 3 over 5. Okay? Times, numerators all together. 2 times negative 4 is negative 8, times 3 is a negative 24. 5 times 5 is 25. So negative 24 25ths is letter A. All right. One more. I'm going to have to get a piece of scratch paper for this one, though. Give me 1 second here. All right. We'll use it like this. So we have the sine of 2x over 1 plus the cosine of 2x. All right. Let's try and give this one a whirl. All right. So I have the sine of 2x, which we already know is this, right? So this is number 2.4. And so I'm going to take the sine of 2. I like to rewrite the problem. 1 plus the cosine of 2x. So these two parts, these 2x parts, are the parts we're going to change. The sine of 2x is equal to this. So 2 sine of x cosine of x. And then I have 1. And then how am I going to change this? That's the question, right? Because it has a couple of different things we can do. Now, I want to cancel some parts out. So I'm going to probably use the 2 cosine squared minus 1, because that'll get rid of this extra 1's here. So this part is going to become 2 cosine squared of x minus 1. Okay, remember that's one of our formulas that we just learned a couple pages ago, or just 1 page ago, I believe. Oh, sorry, excuse me, right here, right? Oh, here's our 3 formulas, okay? 2 cosine squared minus 1, all right? So that's what we're going to use. And let's see where that gets us here. So we have 2 sine of x cosine of x over, my 1's are going to cancel, so I'm left with 2 cosine squared of x. All right, now I can reduce some things, right? My 2's can definitely be reduced, and I can take away 1 cosine here and this squared, and so I'm left with sine of x over cosine of x, which is the same as the tangent of x, right here, letter C. All right. Okay, let's take a look at number 7. For number 7, it says simplify the trigonometric expression cosine of 2x, or the quantity 2x, plus 2 times the sine squared of x. They want us to simplify this expression. Okay, turning back and looking at our cosine formulas again, we definitely are going to want to use this middle one. Cosine of 2 theta equals 1 minus 2 sine squared, because we have a positive 2 sine squared right here. So let's change it to that. So instead of the cosine of 2x, we are going to have 1 minus 2 times the sine squared of x plus 2 times the sine squared of x. These, of course, 2 minus 2 is 0, and we're left with just a 1, which is letter A. We have here the cotangent of theta times the sine of 2 theta. So cotangent, I'm going to change it over to cosine over sine, right? So it's the cosine of theta over the sine of theta times the sine of 2 theta is this, we had it written up here, right? Because we've already been using that one quite a bit. So it is 2 sine of theta cosine of theta, and basically over 1. So we can cancel these, and together then we're left with 2 times the cosine squared of theta. And I have a 1 here. Why do we have a 1 here? Sine of 2 theta is 2 times the sine of theta cosine of theta. All right, so since they want us to basically not have a square, what they're looking to do here is take this formula, which is, hold on, let me make sure I write it down correctly. Cosine of 2, oh my goodness gracious. Cosine of 2 theta, right? We just learned a double angle formula. It's right here on page 30, is equal to 2 cosine squared minus 1. Then we're going to solve for 2 cosine squared, since that's what we have here. And we would see that 2 cosine squared is equal to the cosine of 2 theta plus 1. So the cosine of 2 theta plus 1 is what they want us to do, or solve for, or what they want the answer to be. Honestly, if I were grading it, it's just one step further that's unnecessary. It doesn't say simplify by double addition or whatever, double angle formula. So this would have been sufficient, but this is how they got to the answer that's in the book. They took this formula of my cosine of 2 theta, but they solved for 2 cosine squared and then substituted this in for this and got the answer. Okay? All right. There's a few more here for you to finish on your own. I don't think it goes on to the next page. No. Go ahead and finish these and then meet me back here for the next part of this section. The next part of this section begins on page 34, and it's entitled Half Angle Formulas. We did doubles, now we're doing half. It says formulas for finding trig function values of half an angle measure can be derived from the double angle formulas. You want to look at how they're derived, go right ahead. We're just going to jump up to the formula. It says the half angle formula for cosine is this. The cosine of theta over 2 is equal to plus or minus the square root of 1 plus the cosine of theta divided by 2. Now it says you'll need to determine the quadrant in which the angle lies in order to know the value is positive or negative. Okay, so we need to know our positive sign, negative sign quadrants pretty well. Let's look at this example. If beta is in the first quadrant, okay, everybody's positive in the first quadrant, right? Whose terminal side passes again through 3, 4. Find the cosine of half of beta. Well, the cosine of beta is 3 over 5, right? Adjacent over hypotenuse, 3, 4, 5 triangle. So it's 3 over 5. We plug that into our equation. Remember, we cannot have a square root in the denominator. So we have to make sure we whittle that out, right? Because this is equal to 2 over the square root of 5, right? We cannot have a square root in the denominator. So it's square root of 5 times the square root of 5, or over the square root of 5 is what we have to multiply by. So they ended up with 2 times the square root of 5 over 5. That's how they got to their answer. So remember, no square roots in our denominators. We need to work those out, right? Okay, page 35. Over here on page 35, it says the half angle formula for the sine is plus or minus the square root of 1 minus cosine of theta over 2. Now, these formulas are extremely similar, right? The cosine formula is a positive cosine. The sine formula is a negative cosine or minus cosine. But that's, other than that, they're exactly the same, okay? So use the half angle formula here for this example to find the sine value of, or find the value of the sine of pi over 8. Now, pi over 8, says, can be expressed as 1/2 times pi over 4. Then we use the half angle formula for the sine. So we're taking half of, rather than write it, here they just wrote 1/2 of beta. But here, you know, in both of the formulas, it's theta divided by 2. So basically it's pi over 4 divided by 2 is what they're writing here. So the angle that we're using is the pi over 4 angle. Now, pi over 4 is where? Grabbing my unit circle here, here's my angle pi over 4. I need the cosine value for pi over 4, which is the square root of 2 over 2. Okay, so pi, they put x over 4, but pi over 4 is the square root of 2 over 2, okay? They put that in, they're doing their math, and they end up with a square root inside of a square root. That's crazy. Okay, but that's where it is, okay? It says, since pi over 8 is an acute angle, the value will be a positive root. And so not plus or minus, it will just be the plus, okay? That's very interesting that we have a square root inside of a square root. But again, no square root in the denominator, that would be a no-go, okay? The half angle formula can be used to prove identities as well. Move out of my way, unit circle. Okay. Over here, we're trying to prove an identity. So remember, we don't cross the equal sign when we're proving identities, okay? So prove cosine squared of theta over 2 minus sine squared of theta over 2 equals cosine of theta. Okay, they rewrote it here. They have their half angle formulas punched in, squaring the quantities, right? Remember, when we square a square root, the insides just fall out. So we have 1 plus cosine of theta over 2 minus 1 minus cosine of theta over 2. Okay, remember when we're doing this, this is kind of like a set of parentheses here. Since we're combined, they both have the same denominator, but this negative has to be distributed through. So it actually ends up being, I'm going to write it all out, and then they just combined it, right? So it's the first part, which is 1 plus cosine of theta, and then it's minus 1 plus the cosine of theta, all over 2, right? Now my 1's canceled, and I have a cosine of theta plus a cosine of theta, which is my 2 cosine of theta over 2. My 2's obviously cancel, and I have cosine equals cosine. All right? Okay. The tangent half angle. The half angle formula for the tangent is this. Again, it's only with the cosine. And it's because our tangent is sine over cosine, it's the sine part, which is 1 minus cosine, over the cosine part, which is 1 plus cosine theta, okay? So the tangent of half of theta divided by 2 is plus or minus the square root of that. Looking at the example. If theta is an angle in standard position that terminates in the third quadrant, tangent's positive in the third quadrant, right? The third quadrant looks like this over here. Such that the cosine is negative 4/5. Now remember, the hypotenuse is always going to be a positive number. So how are we getting our negative 4/5? Well, the cosine is what, right? It's adjacent. So this is my negative 4 over the hypotenuse, right? This has to then be a negative 3. It's just the way it is. So find the tangent. Now, I like to draw it out because I want to see what I'm working with. We didn't really need to because we already have the cosine, which is all we needed for this formula, right? For our half tangent formula. So it's basically going to be 1 minus the negative 4 over 5 over 1 plus negative 4 over 5. Now we can't have a minus minus in math, so this becomes a positive, and it ends up being 9/5. 1 minus 4 over 5 ends up being 1/5. We cannot divide a fraction by a fraction, so we have to multiply by the reciprocal. So it looks like, I guess I didn't need to write it that big, 9 over 5 times flip-flop multiply, right? 5 over 1, all under the square root. These cancel, which is how they came up with the square root of 9 plus or minus the square root of 9, which is negative 3 based on the quadrant. It says it terminates in quadrant 3. Half of it, right? The original angle terminates in quadrant 3. But half of that will terminate in quadrant 2, where the tangent is actually negative. So we only want the negative one. Okay, so remember, when we're taking halvesies, the angle that we're actually solving for isn't where we're starting, right? We started here, but halveses will push it back more. Okay? So it's going to be negative 3. All right, let's turn the page. All right, let's take a look at some of these problems here. It says, if theta is an angle in standard position whose terminal side passes through the points 3, 4, evaluate half of tangent. Okay. 3, 4. let's see here. Both of these points are positive, and it's positive 3, positive 4. So we are in the first quadrant, okay? Evaluate the tangent of half. So my tangent is opposite over adjacent, so 4 over 3, right? It's at the point 3, 4, okay? So 4 over 3. And they want a half tangent. So remember, the tangent of theta over 2 is equal to the square root, or plus or minus the square root, of 1 minus the cosine over 1 plus the cosine. Okay, so I need the cosine. What is the cosine in this case? Well, the cosine is adjacent over hypotenuse, and that's going to be 3 over 5. They're using the 3, 4, 5 triangle. So it's going to equal plus or minus the square root of 1 minus 3 over 5 over 1 plus 3 over 5. Now 1 in this case is going to be 5 over 5. So 5 minus 3 is going to be 2 over 5. And then I have down here 5 over 5. 5 plus 3 is 8 over 5. So then I have the square root plus or minus the square root of 2 over 5 times, flip-flop multiply, 5 over 8. My 5's cancel. 2 goes into 2 once, and it goes into 8 4 times. So I have the square root of 1 over 4. Both of these are perfect squares, right? Plus or minus for now. And so I have plus or minus 1/2. The square root of 1 is 1. The square root of 4 is 2. Plus or minus 1/2. It's in standard position. Tangent is positive, so I want the positive, which is letter C. Let's take a look at number 17. For number 17, it says sine squared theta over 2 minus the cosine squared of theta over 2. So we need to go back and look at what those two things equal, right? Again, they don't give us a lot of room, so we got to squeeze it in. The sine squared of theta, of theta over 2 is plus or minus the square root, okay, of 1 minus the cosine of theta over 2. Now, remember, these are squared, so now that that's in there, we're going to square it. And this is then minus, plus or minus the square root of 1 plus cosine of theta over 2, the quantity squared, okay? Remember, when we square something, I might have to get a piece of scratch paper here. When we square something, the square root goes away, right? It's the opposite of taking the square root is squaring something, so it drops away. And also these plus or minuses are going to go away too, because we square something, it's always positive. So this is going to end up with 1 minus the cosine of theta over 2 minus 1 plus the cosine of theta over 2. Since they have a common denominator, we can combine them. I'm trying to fit it on the paper, so here we go. So it's going to be 1 minus the cosine of theta minus, now remember, this minus has to be distributed through. So it's minus 1 minus the cosine of theta all over 2. We won't worry about that. Well, I guess we need to worry about that. Over 2. Okay. This is a positive 1 minus 1, so they're canceled. And a negative cosine minus a cosine is negative 2 cosine of theta over 2. So my 2's cancel, and I'm left with just a negative cosine of theta, which is this letter right here, letter D. All right. So make sure you are checking the back of your book, right? It starts on page 43, all those important formulas, or you can make yourself a cheat sheet, okay? Let's take a look at number 18. If theta is an angle in standard position that terminates in quadrant 3, such that the tangent of theta is 5/12, then the sine of theta. Okay, so we're terminating, I'm going to write it over here. Hopefully that's on page, yeah, okay. In quadrant 3, so that's going to be down here somewhere. Remember that the tangent is opposite over adjacent, so this is 5 and this is 12, but these are going to be negative. And because this is the special 5, 12, 13 triangle, 13 is my hypotenuse, okay? Now, if you didn't know that or don't remember that, then you could have used the Pythagorean theorem, right, to solve for that. Now they want the sine of 1/2 theta. Okay, we wrote the sine of 1/2 theta right here. Obviously don't square it, but that's the formula for it, right? So it's plus or minus the square root of 1 minus the cosine of theta. Well, the cosine is going to be negative 12 over 13 divided by 2. Now, we can't have a minus minus in math, so this is going to become a plus. And we are going to have plus or minus the square root of 1 plus 12 over 13 over 2, all over 2, okay? Now, the 1 is going to become a 13 over 13 because that is 1, right? So I have 13 over 13 plus 12 over 13, all of that divided by 2. Well, 13 plus 12 is 25 thirteenths, right? Divided by 2, square root, plus or minus. Now we cannot divide by a fraction, right? This is basically 2 over 1. We can't divide a fraction by a fraction. So it becomes plus or minus the square root of 25 over 13 times, we're going to flip-flop multiply, or we're going to multiply by the reciprocal, okay? And then have plus or minus the square root of 25 times 1, which is 25, over 13 times 2, which is 26, okay? This then becomes, because 25 is a perfect root, right? It's plus or minus 5 over the square root of 26. We can't have a square root in the denominator, so we're going to multiply both sides, or multiply the top and the bottom, sorry, by 1 in the form of the square root of 26 over the square root of 26. Finally giving us 5 times the square root of 26 over 26. I don't know if that's even legible, okay? Now the question is it positive or negative? We are in quadrant 3, but we're taking the half of that, and the half of that is going to push us up into quadrant 2. And so in quadrant 2, sine is positive, right? All students take calculus. And so the answer is letter D. 5 times the square root of 26 over 26 positive, because we'll be in quadrant 2 for a half angle, okay? Finally, taking a look here at 29. Not 29, 219. It says, it has here the square root of 1 minus cosine of 45 divided by 2. And they're asking us they're just listing a bunch of things here. And so what is it that we're looking for? Well, 22.5 is half of 45. So basically what this is the sine of 1/2, okay, of 45. And 1/2 of 45, because that's what the sine, remember sine is the negative. Half of 45 is 22.5, so the answer is B. All right, go ahead and finish these couple. We only did a couple, not together, a few. Go ahead and finish those, and then meet me back here for this last part of Unit 5. The last section of Book 5, or the last part of Book 5, Section 2, begins on page 37. And it's about converting between products and sums, okay? And it is this word that I forgot to look up how to pronounce, but it's a process of multiplying numbers, right? They used it to change a multiplication number into an adding or subtracting number to make it quicker, right? This was before calculators and whatnot. And so to be able to multiply numbers quickly, they changed it into an addition problem. And then these are what the formulas are, okay? There are, so far, 4 of them right here. So if we have a sine of an angle times the cosine of another angle, we're using this formula, and it seems confusing, but it really isn't. We'll get into the problems in a second. If you're taking a cosine of an angle times the sine of a different angle, so the order matters. Make sure you understand that. Here is that formula. Watch the signs because they do change, okay? If you're taking the cosine of an angle times the cosine of another angle, then here is that formula. And again, watch the signs because they are not all the same. And then you have a sine of an angle times the sine of another angle, and it's this formula, okay? Just like any other time we use a formula, we're going to put in the information that we have and then solve, right? Makes it easy. This example, I highlighted it, but I'm not actually going to go through it. It's multiplying two numbers together and how they used this word that I forgot to look up how to pronounce to solve big multiplication problems using product to sum formulas. I don't know that it's necessary to go through it like this, but let's look at some of these actual problems on the next page. So on page 38, it says here, well, we don't actually, like the example I didn't go over, and plus it's the answers on this page. It's kind of annoying. Anyway, while we didn't go through it, it says we don't actually multiply generally like that anymore because we have calculators, right? But we can use these formulas in trigonometry. So they want us to express the sine of 3 theta times the sine of theta as a sum and difference. And so we set up the formula. We put in our A angle and our B angle into each of the spots, and then we actually just combine, right? So 3 theta minus 1 theta is 2 theta. 3 theta plus theta is 4 thetas, right? And then that's as far as we can go. They distributed the 1/2 through, and that's as far as we can go because we don't know what theta actually is, right? Looking up here, express the cosine of theta times the sine of theta. So it's all about choosing the right formula. This is a cosine times the sine. So the cosine times the sine is 1/2 times the quantity, sine of the quantity theta plus 3 theta, minus sine of the quantity theta minus 3 theta. Okay, so theta plus 3 theta is 4 theta. Theta minus 3 theta is actually negative 2 theta. Okay, because this is 1 minus 3. So the book has a bit of an error here. This is minus 2 theta. We can't have a minus minus in math, right? So it becomes a plus, but it's still a 2. And this should still be a 2, okay? And then they distributed the 1/2 and got 1/2 the sine of 4 theta plus 1/2 the sine of 2 theta, okay? Now the formulas can be not expressly gone backwards, but probably. They don't look the same, right? The following formulas are the sum to product formulas. Now, if we're adding two different angle measures, here is how we can multiply them instead, okay? So again, there are 4 of them, and they look like this. Sine A plus sine beta, sine alpha minus sine beta, cosine alpha plus cosine beta, and cosine alpha minus cosine beta, okay? And they make these formulas. Looking at this example, express the sum of the cosine of theta plus the 4 theta plus the cosine of 2 theta as a product. Well, we need the cosine plus, right? Cosine plus cosine. And it is this formula. Watch your signs because they do change, okay? Actually, it looks like the signs here all stay the same, except this one here has a negative out front. So we've got to watch out for our signs. So it's going to be 2 times the cosine of alpha plus beta divided by 2 times the cosine of alpha minus beta divided by 2. And then we substitute in our values, okay? We have a 40 and a 20, so it's going to be 2 cosine of 4 theta and a 2 theta. 4 theta plus 2 theta divided by 2 times the cosine of 4 theta minus 2 theta divided by 2. And it ends up looking like this. 2 times the cosine of 3 theta times the cosine of, wow, they're really dropping the ball here. Oh, no, I see what happened, okay? This is 4 plus 2, which is 6, right? 6 divided by 2 is 3. Then we have 4 minus 2, which is 2 theta, divided by 2, which is just theta. So that's how they got to this answer. Not a mistake this time. All right, one more example up here where we can use these to prove identities. So here they have the sine of 5t, and I'm sure this has a Greek name. I'm not sure what it is, but plus the sine of 3t over the cosine of 5t plus the cosine of 3t equals the tangent of 4t. Okay. We obviously have product going on here. So if we change it to the sum to product, no, well, this is a sum, yes, sorry. We have a sum here. If we change it to the sum to product formula, then we can solve this, okay? Now, there is a bit of a typo here still because they put the plus in between, and that is not how this works, right? These are to be multiplied together. That's the whole point of the product. That's what was throwing me off here. So this plus shouldn't be here, and this plus shouldn't be here. And as you can see, by the time they got to here, they weren't there, but this plus shouldn't be there, and that plus shouldn't be there. So they've substituted in, right? They have 2 times the sine. What are we doing? We're doing a sine plus a sine. Sine plus sine, okay? So they have 2 times the sine of a plus b, which is 5t plus 3t, times the cosine of a minus b, or 5t minus 3t. In the denominator, it's the cosine plus the cosine, so it's this formula. 2 times the cosine of a plus b over 2 times the cosine of a minus b over 2. In the numerator, 5 plus 3 is 8t's, divided by 2 still. 5t minus 3t is 2t, okay? In the denominator, 5t plus 3t is 8t, divided by 2, and 5t minus 3t is 2t, again, divided by 2. So it ends up being 2 in the numerator times the sine of 4t times the cosine of t over 2 times the cosine of 4t times the cosine of t. Now, the cosines of t can be canceled out, right? Cosine of t is over the cosine of t is 1, right? So that they canceled off. The 2's they canceled off. 2 over 2 is 1. And they're left with the sine of 4t over the cosine of 4t, which is the tangent of 4t. Okay? Other than these errors there, the problem works out pretty good. Let's take a look at problem number 21. We have 1/2 times the quantity, sine of 2 theta plus 7 theta, plus the sine of the quantity 2 theta minus 7 theta. Okay, and parentheses. So they've given us what the sum would look like, okay, and they want us to list what the product is. Now, those, remember, are over here, so it's going to be kind of hard to flip back and forth. So maybe, like I said, maybe make photocopy of the end of the book answers where they give us the setup here. I don't know what page exactly this one is. It starts on page 43. Sum, product to sum, and sum to product formulas are on page 46, okay? But we have a sine of 2 angle measures plus the sine of 2 angle measures. So the sine plus the sine of 2 different angle measures, the first one being positive, the second one being negative, is that sine of alpha cosine of beta, right? That's the setup. It's the first one on your list of formulas. So to write our answer that way, we would have the sine of 2 theta times the cosine of 7 theta. And that answer is letter C, right here. Okay, let's take a look at the next one. The sine of 4x times the cosine of 2x equals what? And so now we're asked to go from a product to a sum, right? All our answers are in sum formation. And this is a sine of 4x times a cosine. So a sine of A, cosine times the cosine of B, is actually what we just did here. So I'm going to use that one as a reference, but instead of the thetas, we're going to put in what we have. So it's going to be 1/2 the quantity sine of 4x plus 2x plus the sine of 4x minus 2x. Okay, that's the formula for this product, sine times a cosine. Okay, since both of these have a 1/2 out front, I know they simplified it all the way down and then distributed their 1/2 just like we did in the work problems back in the book here where we were doing them. So this is the sine of 6x plus the sine of 2x. Okay, and then they multiplied by 1/2, so 1/2 sine of 6x plus 1/2 sine of 2x. Okay, so this is answer A, letter A. All right, let's turn the page and do a couple more. On page 40, let's take a look at problem number 24. They want us to express the cosine of 5m times the cosine of -3m as a sum or difference formula. So we want to find our cosine times cosine formula, and that is 1/2 the cosine of alpha minus beta, okay, plus the cosine of alpha plus beta. All right, so now we put in our information. 1/2 cosine of 5m minus -3m, because remember, this minus is part of the formula, that minus belongs to the 3, plus the cosine of 5m plus -3m. All right, can't have a minus in math, so we change that one to a plus, and we have 1/2 the cosine of, I guess I don't need a parenthesis anymore, 8m plus the cosine of 5m minus 3m, which is 2m. If we distributed our 1/2, it would just be 1/2 cosine of 8m plus 1/2 cosine of 2m. Okay, so 8m plus 2m is letter D. So letter D for number 24. Let's do one more together, 25. We have the cosine of 4 theta plus the cosine of 2 theta over the cosine of 4 theta minus the cosine of 2 theta. So in the numerator here, I'm going to section this off here. We have a cosine plus a cosine. So we're going to change that over because they obviously want us to simplify this to its lowest terms, right? So we're going to change that over to 2 times the cosine of alpha, let me make sure I get my signs right, alpha plus beta, so 4 theta plus 2 theta divided by 2, times the cosine of 4 theta minus 2 theta divided by 2, all over. Now down in the denominator, we have the cosine of 4 theta minus the cosine of 2 theta. So this is a little bit different. It's -2 cosine of, or sorry, not cosine, -2 sine, gotta be careful with these formulas, gotta be careful to transfer them over properly, of 4 theta plus 2 theta over 2 times the sine of 4 theta minus 2 theta over 2. Okay, now let's simplify here what we have going on. So I have 2 cosine, this is 6 theta over 2, or 3 theta, times the cosine of 4 theta minus 2, which is 2, divided by 2, which is just theta, over -2 times the sine of 4 theta plus 2 theta, which is 6 theta, divided by 2, which is 3 theta, and the sine times the sine of 4 theta minus 2 theta, which is 2 theta, divided by 2, which is just theta. Now, my 2's cancel, but don't lose that negative symbol because that needs to stay there, right? That's not going anywhere. And then the cosine over the sine is just going to be the cotangent, right? The cotangent of 3 theta, and the cosine over the sine is also the cotangent there as theta. So remember, tangent is sine over cosine, so cotangent is cosine over sine. So we end up with negative cotangent 3 theta times the cotangent of theta, which is letter A. That might have got cut off a little bit. Letter A is the answer for this one, okay? So for this one, we just substituted in the identities. I keep saying equations, but they're called identities. We substituted in the sum to product identity and then simplified. Okay? All right. Go ahead and finish those, and then we are at the end of this book. Great job. We're also at the end of the semester for now, so we won't be back for a little bit with book 6, or unit 6, I should say. But if any questions come up, do not hesitate to contact me. Otherwise, until next time.